Okay, in this video I'm going to look at problem 46 from chapter 21. I received questions from people in both sections about this problem, and I'm going to put some document on ODTUClass that solves this problem in detail, but I thought that I'll also give you my take on this problem. So here we have a vertical rod, okay, of length L. And this has some uniform charge density lambda, and they are calling the midpoint of this rod to be 0, and we're looking at a point P of distance x from this midpoint P. Okay? And in fact, they are referring to some figure, so we are going to have some coordinate system that looks like this. Okay? Y in the vertical, x in the horizontal. So this x is also the x coordinate of this point P, not just the distance of this from the midpoint O. Right? And they're asking for the electric field at this point P. So what's the electric field at point P? Right. Now, the first thing you might want to try when you see this problem is Gauss's law, right? Because you might think that this is very similar to this infinitely long rod, and this has cylindrical symmetry because, you know, as you go around this rod, everything remains the same. So you might be tempted to just, draw a cylindrical Gaussian surface that has the radius going up to this point P and so on and so forth, but that's not going to work, right? The reason is that this problem does not have cylindrical symmetry. So cylindrical symmetry has two components. One of them is the rotational symmetry around an axis. The other one is translational symmetry along the axis. Okay? So if this was infinitely long, then you would have translational symmetry. Or if somehow we were far from the edges, this would have translational symmetry. Right? As we move along, nothing will change. But because it's finite, it doesn't have translational symmetry. When we move up and down in the vertical, we are going to encounter the edges, and the translational symmetry is going to be broken. We will see something new that we don't actually see when we are close to the center. Right? So the electric field lines are not going to be in the radial direction, and their magnitude is not going to be constant as we move along the y coordinate. This doesn't have cylindrical symmetry. So that is going to fail if you try to do that, but you can still use Coulomb's law. Right? So for Coulomb's law, what you need to do is to take this and divide this into little pieces. So I'm going to call the length of these pieces dh. I'm not going to call it dl because we already have a l in the problem. I don't want to confuse the two. And there is going to be some charge associated with these little pieces. I'm going to call that dq. Okay? Now, before actually attacking this problem, one thing you need to realize, or one thing hopefully you do realize, is that there is a symmetry in the problem. Right? Okay, there is no cylindrical symmetry because it's not translational symmetry, but there is a reflectional symmetry. Right? So the up from this x-axis is the same as down from this x-axis. If I just flip this around, everything will remain exactly the same. Now what this means is that for this point, this is going to produce some electric field that has a vertical and horizontal component, but there is a corresponding point over here that's going to produce an electric field of identical magnitude, but the vertical components of these two are going to cancel each other, and we're going to end up with a purely horizontal field. Right? So this you could immediately tell from the reflectional symmetry on this x-axis. The electric field could not be pointing up or down at that point because that will break the reflectional symmetry. So electric field is going to be purely in the x direction, which means that I just need to calculate the x component of the electric fields. Right? So if I'm trying to calculate the electric field for this one, I actually only need to calculate the x component of the electric field. Right? So let's just combine this, and this angle is also going to be theta because these are inverse angles. So the electric field is just going to be the x component of the electric field, and this is going to be the integral of the x component of each little infinitesimal charge lying along this rod. Okay? Now I can't do this. Sorry. Right. So this will be wrong because electric field is a vector. You cannot find the magnitude of a sum by summing up the magnitudes. That doesn't work. But it does work for components. So we first express this in terms of components, and then for the components we can do this decomposition. Right? So the parts of a component is going to add up because those are just scalar numbers. Right? But this one here is just going to be, for this figure, it's the x component, it's going to be cosine theta times dE. Okay, now I need to write that dE in terms of this contribution from this charge, and for that I will need a distance. Let's call this distance r, and that dE is going to be dq divided by, well, it's 4 pi epsilon naught r square, and that r square we are going to express in terms of our variables, right? And there's this issue of expressing dq. Now what's that? dq is going to be some lambda times the length of this little piece. Okay. Now I want to take this integral, and as I'm taking the integral, what I want to do is I want to cover this rod. I want to take into account the contribution of each and every part, and nothing else. Right? That's my aim here. So how do I cover this rod? Well, by moving along the y-axis, starting from y equals minus L over 2, reaching to y equals L over 2. Right? So what does this tell us then? So first of all, let's look at this r. Now what would r be? As I move along this x-axis, so I'm looking at this one little element. Okay? So how can I express this r in terms of where I am on the rod? Now, how would you express where you are on the rod? Okay? Well, by the coordinate of this little point. Okay, that little point is going to, so I can express it as the coordinates of this point, and that point actually just as a y-coordinate. The x-coordinate is 0. Okay? So, and that a y-coordinate also gives the length of this right edge on this right triangle, and this edge is already x, so I can say that r square is x square plus y square. Okay? Now this is a little bit of a perhaps confusing thing because this x is a constant. It's just the distance of this point from the midpoint of this rod, but that y is a variable. Okay? So that is the coordinate of this point that I'm moving around. Okay? That x is not it's not the coordinate of this point. So perhaps it will be, better to write it this way. Unfortunately, the book is kind of forcing you to make these choices because they are giving you this, and then it leads to some confusion. But maybe if you write it this way, it's going to be less confusing. But I will keep the book's convention so we actually get the answer in the correct variables. Okay, so that's going to be our distance squared, x squared plus y squared, keeping in mind that x is actually a constant. Now what about this dh? Now this dh is the length of this little piece, and it's purely along the y-axis, y-coordinate, right? So this means that this dh is in fact, for this case, equivalent to dy. Right? So if it was tilted or something like that, it would perhaps have x component, or if it was along the x-axis, it would just be dx. But here it corresponds to moving along the y-axis in infinitesimal steps. And how do you move along the y-axis in infinitesimal steps? By adding dy to your y, okay, to wherever you are. So it allows you to move from this y to y plus dy. So this dh must be dy indeed. Okay? So this is going to be lambda times dy. Okay? Now, these arguments that I'm making is to really justify what I'm going to write down. Okay, these are not rigorous. If you want rigorous stuff, you should actually look at the calculus book and talk to a mathematician, something like that. But the fact that I write these down in terms of variables, it comes from experience. Okay? So you solve some problems, and then eventually you develop this experience. Okay, so let's write this down though. All right. So we are going to have some cosine theta lambda dy divided by 4 pi epsilon naught x squared plus y squared. And I'm covering this rod, and that will correspond to y starting from minus L over 2 to y going to L over 2. So I can, at this point, also substitute these. Now this integral has to be taken over the y-axis. I'm not going to write it down. It's just something to keep in mind. It doesn't, you don't go this way or something like that. Okay, now to take this integral, first we take the constant factors out. So let's do that. Lambda over 4 pi epsilon naught. These are constants. I can take this out. I cannot take this x squared plus y squared out because the y is a variable as I move along. This r, distance r, is going to change. That's evident. I can't take this cosine theta out either. Right? As I move along this road, this theta is going to change. It's going to start at some negative angle over here, and it's going to end up some positive angle over there. So I can take the cosine theta out, which means that I need to express this in terms of y, so I can actually take the integral. Otherwise, I can't take the integral. And now, that's not too hard to do. That cosine theta, if you look at this right triangle, is going to be adjacent over the hypotenuse. So adjacent is x, over the hypotenuse is x squared plus y squared to a half. Okay, so you can write it this way. Now another way to do this, to approach this problem, is to express y in terms of theta. Okay? I'm not going to do that. It's already done in the example in the book for the infinite rod. But that's also possible. And in fact, it turns out that it's actually more practical in some sense for that problem, for the infinite rod problem, because it saves you taking some integral. It turns the integral into a trivial one. But here I'm just going to go with cosine theta equals this. Now this is also a constant, so I can take that out. Okay. So this is from minus L over 2 to L over 2. So I have dy in numerator. And in denominator, I have x squared plus y squared and the square root of x plus y squared. So that comes to x squared plus y squared to 3 halves. Okay. Now, how do you take this integral? Now, I'm not going to take the integral. I'm just going to look this up. It is in our book. There's an appendix, Appendix B, that gives you some integrals and derivatives. And you can look this up. It's in section B4 of that appendix. You need to use the so-called trigonometric substitution. Okay. Trigonometric substitution. Okay. So you can look this up, perhaps find some resource on the internet, or you can look at your calculus books, or you can ask your calculus instructor for some resources on how to do this. But the way to solve that solid integral is by trigonometric substitution. I don't know if integration by parts would work. Perhaps it would, but I suspect not. All right, but if you look this up, you're going to find that this is going to be, so let's write the constants, lambda x, 4 pi epsilon naught. You're going to have, so when you're looking this up from the appendix in the book, be careful. All the integrals are given there in terms of the variable x. Here our x is a constant. The constant given in the book is a. Okay, and x is the variable. So you need to really make a substitution for this to work. But if you do it correctly, what you're going to get is this is y over x squared plus y squared to a half, and from minus L over 2 to L over 2. Okay? This is the result that you get. And then you need to substitute these and take the difference. And you will notice that substituting these is just going to pick up a negative sign because there is a square of this here. It doesn't matter whether you put L over 2 or minus L over 2. And then when you subtract it off, it's essentially substituting this and multiplying by 2. Right? So that's what I'm going to do. So lambda x 4 pi epsilon naught. I will substitute L over 2, but I will just say 2 L over 2 by x squared plus y squared to a half. These go away, and hopefully we actually have the expression over there. This is going to be L squared over 4 to a half. And to make it look more like the expression given in the book, you need to take this 1/4 out of the square root. 1/4 out of the square root becomes a half, so that a half is going to cancel half of this 4, it's going to become just 2. So we can write this as lambda xl divided by 2 pi epsilon naught x square plus, 4x square plus L square to a half. Okay? And finally, we can cancel this x with one of the x's in the denominator, and we get the expression that's given in the book. Okay, it's a little bit tedious, but a straightforward problem, and perhaps the nasty part for you is taking this integral. As you have seen, I didn't take the integral, I looked it up. And if you want to take it honestly, you can do this trigonometric substitution. For this problem, you could also, express this y in terms of theta is done in the book for the example, for the infinitely long thin rod. But here it's going to be a little bit nasty because you're going to also need to change the limits of the integral using arctangents and so on and so forth. Right, so it can be done, but it is sort of like doing trigonometric substitution for a definite integral, whereas it's much easier to do the trigonometric substitution for indefinite integral and then putting the limits. Right? So this expression as an indefinite integral is something well known, so you can just use that.